go. In this lecture, we'll prove Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CVN. In the drawing we have triangle ABC. The length of side AB is C units, side AC equals to B units in its length, side BC equals to A units in its length. In addition, line segment VD equals to M units and line segment DC equals to N units, and the CVN in this triangle ABC is AD, and the CVN AD equals to D units in its length. Repeat again, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CVN. Okay, the length of the CVN here is D units. And according to Stewart's theorem, B squared times M plus C squared times N equals to A. We open brackets. Inside the brackets we have D squared plus M times N. Again, B squared M plus C squared N equals to A. We open brackets. Inside the brackets we have D squared plus M times N. So we have to prove that this equation is true. We prove that this equation is true in two different methods. So we start with the first method. In the first method, we do a construction. That is to say, from the vertex A, we draw perpendicular on BC. Repeat again, from the vertex A, we draw perpendicular on side BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. In addition, we define this line segment ED as X. We'll also define the length of this line segment AE as H. And what is the length of line segment EC? The length of line segment EC equals to ED plus DC. EC equals to ED plus DC. ED equals to X, DC equals to N, therefore EC equals to X plus N. EC equals to X plus N. Line segment EC equals to X plus N units in its length. And what is the length of line segment BE? The length of line segment BE, from the drawing it is very easy to see that BE equals to BD minus ED. Again, BE equals to BD minus ED. I write it down. BE equals to BD minus ED. Okay, so BE equals to BD equals to M units. Let's see it from the drawing. And ED equals to X. So B equals to BD, this is M units, minus ED, this is X. So in the conclusion, we found out that BE equals to M minus X units in its length. This line segment BE equals to M minus X units in its length. In the next step, we'll implement the Pythagoras theorem, the green right triangle AED. Repeat again, we'll implement the Pythagoras theorem on the green right triangle AED. Here by PT is the evaluation from Pythagoras theorem. According to the Pythagoras theorem, in the right triangle, triangle AD, or in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. I repeat again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle AD is AD, therefore the square of the hypotenuse is AD square. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AE square plus ED square. Repeat again, in the right triangle, triangle AD square, according to the Pythagoras theorem, AD square equals to AE square plus ED square. Okay. AD equals to d units in its length, therefore AD square is d square, and it is equal to AE square. AE equals to h units in its length, therefore A square is h square, plus ED square. ED equals to x, therefore ED square is x square. In conclusion, we found out that according to the Pythagoras theorem, in the right triangle, triangle AD, d square equals to a square plus x square. In the next step, we'll focus on the right triangle AEC, this right triangle AEC. And we will implement the Pythagoras theorem on this right triangle, triangle AEC. According to the Pythagoras theorem, on the right triangle AEC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is AC, therefore the square of the hypotenuse is AC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AE square plus EC square. So according to equation number 1, we found out that in the right triangle AC, AC square equals to AE square plus EC square. The hypotenuse AC is D, therefore AC square is D square, and it is equal to AE square. AE is H, therefore AE square is H square, plus EC square. EC equals to x plus n units in its length, therefore EC square is x plus n square. So actually, according to equation number 1, in the right triangle AC, we found out that d square equals to h square plus x plus n square. We will open the brackets on this side of equation number 1, and we will get that according to equation number 1, d square equals to h square plus x plus n square equals to x square plus n square plus 2 times x times n. Here we have, in this equation number 1, we have h square plus x square. H square plus x square equals to d square. So according to this equation, so we substitute h square plus x square in this equation, equation number 1, by d square. Here the hypotenuse AC equals to B square. Therefore, the square of the hypotenuse AC square is B square. It is B square. Again, the hypotenuse AC in the right triangle AC is B, therefore the square of the hypotenuse AC square is B square. So it is B square is equal to A square plus A square plus N square plus 2 times XN. So B square equals to H square plus X square is D square plus N square plus 2 times X times N. So according to equation number 1, we found out that B square equals to D square plus N square plus 2 times Xn. In the next step, we'll implement the Pythagoras theorem on the right triangle AEB. This the right triangle AEB. Okay, so we'll implement the Pythagoras theorem on the right pink triangle, triangle AEB. So in the right pink triangle, triangle AB, by PT is the version of Pythagoras theorem. In the right pink triangle, triangle AEB, the square of the hypotenuse equals to the sum of the source of the perpendiculars. The hypotenuse is AB, therefore the square of the hypotenuse is AB square. And it must be equal to the sum of the source of the perpendiculars. That is to say, it must be equal to AE square plus BE square. I repeat again, in the right pink triangle, triangle AB, according to the Pythagoras theorem, AB square equals to AE square plus BE square. This is equation number 2. The hypotenuse AB in the right triangle ABE is equals to units itself. Therefore AB square is C square. That is equal to AE square. AE is H, therefore A square is H square plus BE square. We already found out that BE equals to M minus X here, therefore BE square is M minus X square. Repeat again, in the pink right triangle AEB, according to the Pythagoras theorem, C square equals to H square plus M minus X square. We'll open the brackets of this side of equation number 2 and we get that according to equation number 2, C square equals to H square plus M minus X square. According to the algebraic identity that A minus B square equals to A square plus B square minus 2 times AB, we get that A minus X square equals to M square plus X square minus 2 times M times X. Again, here we have H square plus X square in this equation number 2, and we have already found out that H square plus X square equals to D square, so we substitute H square plus X square in this equation, equation number 2, by D square. And we get that according to this equation number 2, c squared equals to a squared plus x squared is d squared plus m squared minus 2 times mx. This is equation number 2, and we already found out that according to equation number 1, b squared equals to d squared plus n squared plus 2 times x times n. Okay. In the next step, we'll create equation number 3 in the following way. In the first step, we'll multiply equation number 1 by n. In the second step, we'll multiply equation number 2 by n, and then we'll add the two equations together. This will be equal to equation number 3. Again, we'll multiply equation number 1 by n, then we'll multiply equation number 2 by n, then we will add the two equations with each other. This will give us equation number 3. Okay, so we'll do it in 2 steps. First of all, we'll multiply on the right side of the equation number 1 and 2, and then we'll multiply the left side. Okay, so we'll multiply the right side of equation number 1, this is the right side of equation number 1, by m. So it is m, inside the brackets we have d squared plus n squared plus 2 times x times n in the next step we multiply the right side of equation number 2 by n. This is the right side of equation number 2, we multiply it by n. So inside the brackets we have d squared plus m squared minus 2 times mx and it must be equal to the multiplication of the left side of equation number 1 by m. In the left side we have only b squared, so it is mb squared plus the multiplication of the left side of equation number 2 by n. So it is, we have only c squared in the left side of equation number 2, so it will be nc squared. Okay. So in the next step, we'll open the brackets of this side of equation number 3. And we'll get that according to this equation, equation number 3, we open the brackets of this expression. M times d squared is md squared plus m times n squared is mn squared plus m times 2xn is 2xmn. We'll open the brackets also of this expression. So here n times d squared is nd squared plus n times m squared is nm squared plus n times minus 2mx is minus 2x mn. And it must be equal, of course, to mb squared plus nc squared. So actually, this is equation number 3 after we open the brackets. So in this side of equation number 3 we have plus 2xmn minus 2xmn is 0. So those two expressions will get cancelled. What is left from equation number 3 after we cancel the two expressions? We have here md squared plus mn squared plus nd squared plus nm squared. equals to mb squared plus nc squared. In the next step, we'll take out d squared as a common factor from d squared and also from nd squared. So here, what is left from md squared after we took from it d squared as a common factor? What is left is actually m. And what is left from nd squared after we took from it d squared as a common factor? What is left is actually n. And we also take a common factor mn out from this expression and from this expression. So what is left from nm squared after we took from it nm is a common factor? What is left is actually m plus what is left from mn squared after we took from it mn as a common factor. What is left? It's actually n. And it is equals to mb squared plus nc squared. In the next step, we take out m plus n as a common factor from those two expressions. So m plus n is taken out as a common factor. What is left from d squared plus m plus n after we took from it m plus n as a common factor? What is left is actually d squared. And what is left from mn times m plus n after we took from it m plus n as a common factor? What is left is actually mn equals to mb squared plus nc squared. Actually, m plus n equals to a. It is very easy to see it from the drawing here. BC, side BC equals to A units in itself according to our definition, but BC also equals to BD plus DC. Again, BC equals also to BD plus DC. That is to say, BC equals to BD that is n plus DC that is n. So from one side, BD equals to A, from the other side, BC equals to n plus n. Therefore, n plus n equals to A. So we substitute m plus n in equation number 3 by a. And we get that according to equation number 3, m plus n is a. Here inside the brackets we have d squared plus mn. And it is equals to b squared m plus c squared n. And this is exactly Stewart's theorem. So we proved Stewart's theorem in the first method. In the next step, we'll prove Stewart's theorem in the second method. In the second method, we define this angle ADB as theta. So the adjacent angle ADC, this adjacent angle must be equal to 180 degrees minus theta. According to rule number 1, that the sum of the angles on a straight line is equal to 180 degrees. BC, side BC of triangle BC is absolutely straight line. So if we focus on the upper side of the side of the straight line BC at point D, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of BC at point D? Here we have angle theta plus the missing angle ADC. In total they must be equal to 180 degrees. So the missing angle theta must be equal to 180 degrees minus theta. Why? Because 180 degrees minus theta plus theta equals to 180 degrees, exactly according to rule number 1. In the next step, I'll present to you, we'll implement the law of cosines in triangle ABD, in the great triangle ABD. This is the great triangle ABD, and we'll also implement the law of cosines in the pink triangle ADC. So I will remind to you quickly what is the law of cosines. First of all, the law of cosines is true in any triangle. So this is triangle ABC. That could be any triangle. We know that the length of side AB is A units, side AC equals to B units in itself, and finally side BC equals to C units in itself, and this angle BAC equals to theta. Then, according to the law of cosines, the following equation in this triangle ABC is true: that C square equals to A square plus B square, A square plus B square, C square equals to A square, C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. Okay, here. So if we add to this equation 2 times AB cosine theta, we get that C square plus 2 times AB equals to A square plus B square. Then if we subtract from this equation C square, we get that 2 times AB equals to A square plus B square minus C square. Then we will divide this equation by 2 times AB, and we will get finally that cosine theta equals to A square plus B square minus C square over 2 times AB. So in this triangle ABC, cosine theta equals to A square plus B square minus C square over 2 times A times B. We will implement the law of cosines in the great triangle ABD. So in the great triangle ABD, according to the law of cosines, we'll get that cosine theta equals to m squared plus d squared minus c squared over 2 times m times d. Actually, this equation number 1, is the implementation of the law of cosines in the great triangle ABD. Cosine theta equals to m squared plus d squared minus c squared over 2 times a m times d. In the next step, we will implement the law of cosines in the pink triangle ADC. According to the law of cosines, in the pink triangle ADC, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times d times n. Cosine in the pink triangle ADC, cosine 180 degrees minus theta equals to d squared plus n square minus b square over 2 times d times n. According to the trigonometric identity, that cosine 180 degrees minus theta equals to minus cosine theta. We substitute cosine 180 degrees in this equation number 2 by minus cosine theta, and we'll get that minus cosine theta according to equation number 2 minus cosine theta equals to d squared plus n squared minus b squared over 2 times d times n. In the next step, we'll multiply this equation number 1 by minus 1, and we'll get that according to equation number 1, cosine theta times minus 1 is minus cosine theta, and it must be equal to, here we multiply also this side of the equation by minus 1, so here we have minus, we'll open the brackets, inside the brackets we have m squared plus d squared minus c squared. We close the brackets here and divided by 2 times m times d. So we have here two different expressions for minus cosine theta. So in the next step we get equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 1 equals to minus m squared plus d squared minus c squared over 2 times m times d, and it must be equal to minus cosine theta according to equation number 2. So minus cosine theta according to equation number 2 equals to d squared plus n squared minus b squared over 2 times d times n. In the next step, we will multiply this equation number 3 by 2d, and we get that according to equation number 3, we multiply this side by 2d. So we have here 2d over 2d is 1, so 2d will get cancelled. So in the denominator we're left only with m. The numerator didn't change, it will stay as minus m squared plus d squared minus c squared, and it is equal to here 2, we multiply this side also by 2d, so 2d over 2d is 1, so in the denominator we left only with n. The numerator didn't change, the numerator remains as d squared plus n squared minus b squared. In the next step, we will cross multiply this equation number 3, and we get that according to equation number 3, minus n. Inside the brackets we have m square plus d square minus c square equals to m times, inside the brackets we have d square plus n square minus b square In the next step, we'll open the brackets of both sides of this equation, equation number 3. And then again, that according to this equation, equation number 3, minus m times m square is minus nm square. Minus n times d square is minus nd square, and minus n times minus c square is plus nc square, equals to, we will open the brackets of this side of equation number 3 also. So m times d square is md square, plus m times n square is mn square, plus m times minus b square is minus mb square. In the next step, we add to this equation, equation number 3, nm square. So in this side of equation number 3, we have nm square minus nm square is 0. We also will add to this equation, equation number 3, nd square. So nd square minus nd square is 0. And finally we subtract from this equation, equation number 3, nc square. So here, in this side of equation number 3, we have nc square minus nc square is 0. So in total, in this side of equation number 3, in total we have 0. And it's equal to, we also have to do the same operation on the other side, of course, of equation number 3. On the other side of equation number 3, we have already had the expression of md square plus mn square minus mb square. So we have to add to this side of equation number 3 nm square, and we also have to add of this side of equation number 3 nd square, and we also add have to subtract from this equation, equation number 3, nc square. Okay. In the next step, we take out d square as a common factor from md square and also from nd square. So what is left from md square, what we took from it, d square as a common factor, what is left is actually m, plus what is left from nd square, what we took from it, d square as a common factor, what is left is actually n. And we also take mn as a common factor from this expression and also from this expression. So what is left from nm square after we took from it nm as a common factor, what is left is actually m, plus what is left from mn square after we took from it mn as a common factor, what is left is actually n. And we also here minus mb square minus nc square equals to 0. In the next step, we'll add to this equation number 3, mb squared, and also nc squared. And we get that in this side of equation number 3 we have d squared m plus n plus mn m plus n. So here m minus mb squared plus mb squared is 0, plus nc squared minus nc squared is 0, and it is equal to mb squared plus nc squared. The next step, we'll take out m plus n as a common factor from those two expressions. So what is left from d squared times m plus n after we took from it m plus n as a common factor? What is left is actually d squared. And what is left from m plus n times mn after we took from it m plus n as a common factor? What is left is actually mn. And is equal to mb squared plus nc squared. Okay, we already found out in the first method that m plus n equals to a, so we substitute m plus n in this equation number 3 by a, and we get that here m plus n is a, and inside the brackets we have d squared plus mn, it equals to b squared m plus c squared n. Okay, and this is exactly Stewart's theorem. So we succeeded to prove Stewart's theorem in the second method. In the next step, I'll summarize the lecture. We'll start with the first method, of course. So in this lecture we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its cVN. So in this is triangle ABC, side AB equals to C units in its length, side AC equals to V units, side BC equals to A units, and the cVN in this triangle is in triangle ABC is line segment AD. The cVN AD equals to D units in its length. In addition, we know that line segment VED equals to M units and line segment DC equals to N units. I repeat again, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its cVN. And according to Stewart's theorem, b squared times m plus c squared times n equals to a, we open brackets, inside the brackets we have d squared plus m times n. Again, b squared m plus c squared n equals to a, we open brackets, inside the brackets we have d squared plus m times n. We prove this, that this equation is true in two different methods. In the first method, we did a construction, that is to say from point A we draw perpendicular on BC. That is to say this again equals to 90 degrees, this again equals to 90 degrees according to our construction. So we define the touching point of the perpendicular from point A and BC as E. Then we define line segment AE as h. We define the length of line segment ED as x. Here, line segment EC, the length of line segment EC equals to ED plus DC. ED is x, DC is n. Therefore, ED equals to x plus n units in its length. What is the length of line segment BE? From the law, it is already to see that BE equals to BD minus ED. Again, BE equals to BD minus ED. BD is m, ED is x. Therefore, in total, BE equals to m minus x units in its length. Again, BE equals to m minus x units in its length. Then we implemented the Pythagoras theorem on the right green triangle, triangle AED. On the right green triangle, triangle AED, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AD, therefore the square of the hypotenuse AD is square, is AD square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AE square plus AD square. Repeat again, in the right green triangle, triangle AED, AD square equals to AE square plus AD square. Okay? So here, AD equals to D units in its length. AE equals to H units in its length, and ED equals to X units in its length. Therefore, we get that D square equals to H square plus X square. Then we implemented the Pythagoras theorem on the triangle, on the right triangle, triangle AC. According to the Pythagoras theorem, on the right triangle, triangle AC, AC square equals to EC square plus AE square. Again, AC square equals to AE square plus EC square. Repeat again, the right triangle, triangle AC square equals to AE square plus EC square. Okay, here. AC equals to B units in its length, AE equals to H units in its length, therefore, and also EC equals to X plus N units in its length. Therefore, we get here that B square equals to H square plus X plus N square. In the next step, we open the brackets of this side of equation number 1 and found out that according to equation number 1, B square equals to H square plus X plus N square. X plus N square equals to X square plus N square plus 2 times X times N. Okay, so here we have this equation number 1, x square plus h square, and h square plus x square equals to d square. So we substitute h square plus x square in this equation number 1 by d square, and found out that b square equals to h square plus x square is d square plus n square plus 2 times xn. Then we implemented the Pythagoras theorem on the pink right triangle ABE. On the pink right triangle ABE, according to the Pythagoras theorem, AB square equals to AE square plus BE square. Again, AB square equals to AE square plus BE square. Here, AB square equals to AE square plus BE square. Here, AB equals to C units in its length, AE equals to H units in its length, and BE equals to M minus X units in its length. Therefore, we get that, according to equation number 2, C square equals to H square plus M minus X square. We open the brackets on this side of equation number 2, we found out that m minus x square, according to the algebraic identity, that m minus x square equals to m square plus x square minus 2 times mx. We get that m minus x square equals to m square plus x square minus 2 times mx plus s square equals to c square. Again, here h square plus x square equals to d square according to this equation, and therefore we substitute h square plus x square by d squares. And we got that c square equals to h square plus x square, that is d square, plus m square minus 2 times mx. Okay, so we have here according to equation number 2, c squared equals to d squared plus m squared minus 2 times mx, and we already found out that according to equation number 1, b squared equals to d squared plus n squared plus 2 times xn. Then we created equation number 3. According to the following way, we multiplied the equation number 1 by m, then we multiplied the equation number 2 by n, and then we added the two equations together, and this created the equation number 3. And we did it in two steps. In the first side, we multiplied the right side of the two equations, and then we multiplied the left side of the two equations. So here, in the first step, we multiplied the right side of this equation number 1 by m. So this is the right side, we multiply it by m. So it is m. Inside the brackets we have b squared plus n squared plus 2 times xn. Then we multiply the right side of equation number 2 by n. So it is n times d squared plus m squared minus 2 times mx. And it must be, so again, n times d squared plus m squared minus 2mx, and it must be equal to the multiplication of the left side of equation number 1 by m. In the left side of the equation number 1 we have b squared, so it is mb squared plus the multiplication of the left side of equation number 2 by n. We have only c squared on the left side of equation number 2, so it is nc squared. Then we open the brackets of this side of equation number 3. We have here m times d squared is md squared, m times n squared is mn squared, and n times 2xm and 2xn is 2xmn. We also open the brackets of this expression. N times d squared is nd squared, n times m squared is nm squared, and finally n times minus 2mx is minus 2xmn. It is equal to mb squared plus nc squared. So this is the equation number 3 after we open the brackets, and again it must be equal to mb squared plus nc squared, of course. So this is equation number 3 after we open the brackets. We have plus 2xmn minus 2xmn is 0, so those two expressions will get cancelled, and we left only with mb squared plus mn squared plus nd squared plus nm squared equals to mb squared plus nc squared. Then we took out d squared as a common factor out from nd squared and also from md squared, so inside the brackets we left only with m plus n. Then we took out nm as a common factor from this expression and from this expression, so inside the brackets we left only with m plus n, and it is equal to mb squared plus nc squared. Then we took out m plus n as a common factor from those two expressions, so inside the brackets we left only with d squared plus mn, and it is equal to mb squared plus nc squared. And here I repeat again that m plus n equals to a. It is very easy to see it from the drawing that m plus n equals to a. From one side, side BC of triangle ABC equals to a units. From the other side, BC equals to m plus n. Therefore, a equals to m plus n. So we substituted m plus n in this equation number 3 by a, and we found out that m plus n is a. Inside the brackets we have d squared plus mn equals to b squared m plus c squared n. Okay, this is actually Stewart's theorem. In the next step, we proved Stewart's theorem according to the second method. In the second method, we defined angle ADB as theta. Therefore, the adjacent angle ADC must be equal to 180 degrees minus theta according to rule number 1. Then we plotted the law of cosines in the green triangle and also in the pink triangle. What is the law of cosines? The law of cosines is for any triangle. So this is triangle ABC, that could be any triangle. The length of side AB is A units, side AC equals to B units in its length, and side BC equals to C units in its length, and this angle BAC equals to theta. According to the law of cosines, in this triangle ABC, that could be any triangle, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay, then we added to this equation 2 times AB cosine theta, and found out that 2 times AB cosine theta plus C square equals to A square plus B square. Then we subtract from this equation C square. And we got that 2 times AB cosine theta equals to A square plus B square minus C square. Then we divided this equation by 2 times AB, and we found out finally that cosine theta equals to A square plus B square minus C square over 2 times AB. Again, in this triangle ABC, cosine theta equals to A square plus B square minus C square over 2 times A times B. We implemented the law of cosines in the green triangle ABD, according ABD. In the green triangle ABD, according to the law of cosines, cosine theta equals to D square plus M square minus C square over 2 times D times M. Repeat again, cosine theta equals to M square plus D square minus C square over 2 times M times D. Then we implemented the same law, the law of cosines, in the pink triangle ADC. In the pink triangle ADC, cosine 180 degrees minus theta equals to D square plus N square minus B square over 2 times D times N. And repeat again, in the pink triangle ADC, cosine 180 degrees minus theta equals to D square plus N square minus B square over 2 times D times N. Then we have the trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta. Therefore, we multiplied cosine 180 degrees minus theta by minus cosine theta in equation number 2, and found out that minus cosine theta equals to D square plus N square minus B square over 2 times D times N. Then we multiplied equation number 1 by minus 1, and we got that cosine theta times minus 1 is minus cosine theta, and we multiplied also this side of the equation by minus 1, so we have minus, we open brackets, inside the brackets we have M square plus D square minus C square over 2 times MD. So we have two different expressions for minus cosine theta. Therefore, we created equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 1 equals to minus M square plus D square minus C square over 2 times MD. It must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 equals to D square plus N square minus B square over 2 times Dn. We multiply this equation by 2D. So this side we multiplied by 2D. 2D over 2D is 1, so in the denominator we left only with M. The numerator didn't change. It states as minus M square plus D square minus C square. We multiplied also this side of the equation by 2D. 2D over 2D is 1, so in the numerator we left only with N. The numerator didn't change. It is D square plus N square minus B square. Then we cross multiplied this equation number 3, and we got that minus M times M square plus B square minus C square equals to M D square plus N square minus B square. Then we open the brackets on both sides of this equation number 3, and found out that minus N M square minus N times D square is minus N D square, and as minus N times minus C square is plus N C square, and it is equal to M times D square is M D square, M times N square is M N square, and M times minus B square is minus M B square. Then we added to this equation number 3 N M square. N M square minus N M square is 0. We added also N D square. N D square minus N D square is 0. We subtracted N C square, so N C square minus N C square is 0. So in this side of the equation we left with nothing. On the other side of the equation, we have already add MB square plus NM square plus MB square. So we have to add to this equation, to this side of the equation number 3, NM square. We also have to add ND square, and we have to subtract NC square. Then we took this square as a common factor from MD square and also from ND square. Inside the brackets we left with only with M plus N. Then we took out Mn as a common factor from those two expressions. So inside the brackets we left only with M plus N minus MB square minus NC square equals to 0. Then we added to this equation number 3 MB square plus NC square. So in this side of the equation we have D M plus N plus Mn N plus N equals to MB square plus NC square. Then we have here, we took out M plus N as a common factor out of those two expressions. So inside the brackets we left only with D square plus Mn equals to MB square plus NC square. We already found out that a plus n equals to a, so we substitute a plus n in this equation and equation number 3 by a, and found out that here a times d squared plus mn equals to mb squared plus nc squared. Again, a times d squared plus mn equals to b squared m plus c squared m. So we succeeded to prove Stewart's theorem in 2 different methods. Okay, thank you very much.